All right, everybody, it's Mr. Chen coming back at you again. We are on kind of like the second last unit, and what's really going on is um, we got to finish exponential functions. We got to look at what the graphs look like, and some applications of it. And Ms. K and I have found a way to try to simplify it into just two lessons, which we're going to do just this week, and see if we can wrap up this exponential function stuff. Okay. Our goal is so that students can see what a graph of an exponential function is, and also be able to write out an equation that models a graph where you have an exponential growth or even a decay situation. But we're going to start with this. Okay. It says lesson 1, model data with exponential functions. And it reads, Jamie, investigate. Jamie cut a sheet of paper in half. He placed the half sheets on top of each other and then cut those in half. And he continued the process until the paper became too thick to cut. It says here, determine the number of pieces he had after 0 all the way to 5 or 6 cuts. Okay, so if you look over here, right, sorry about that. So we got the number of cuts going down the list on the left-hand side, right? So you guys know that if we were to plot this stuff, we are talking about like, on the graph here, the x values and the y values, right? Because as the x values change, there's something going on with the y values. And here's just a really quick way of doing it. When you got 0 cuts on the piece of paper, how many pieces of paper you got? 1. You got 1 cut going down the middle, you end up with 2 slices, right? 2 pieces of paper. You take your second, so you fold the paper on top of each other, right? And then you cut again for your second cut, and you end up with 4. Okay, and you take those 4 sheets of paper, stack them on top of each other, cut them again, and this time this will make your third cut, which will give you 8. Okay, let's say take those 8, stack them on top of each other, and cut it for a 4th time. This will give you 16. If you are tracking, then this is the rest. Okay, and okay, so we end up with like 64 pieces of paper after 6 cuts. Okay, 6 cuts and make 64 slices of paper, all equal size too. Now you got to create a graph of the data. So we got to put in the sides, labeling in the axes, and we also have to use a proper scale. So let's see what that looks like. Okay, something like this, right? Of course, from up here, we know that the x values is the number of cuts and the y values is the number of pieces of paper. So there's your y and there's your x, right? And that'll, in theory, keep on going, but we know that physically you're limited because you can't just keep on cutting those sheets of paper. They get too thick and it's too hard to cut. So the next thing we got to do is we got to label this, right? So at 0, there was 1. At 1, there was 2. At 2, there was 4. At 3, there was 8. 4, 16, 32. 6 is 64. And the plots look like this. And we got one more step we got to do, which is to come in and draw in what that line, more like a curve now, should looks like. Okay. All right. So if I can just kind of like tell you the nature of this growth chart, right? We have something where the number of pieces of paper we're going to get as we put in more and more cuts is going to skyrocket, right? And you can see that the number is actually doubling. So when you double the number 1, it becomes 2, but you double the number like 64, you get 128. So that's really, really going to jump, and it's going to jump fast, okay? So just a quick question. How far will the graph continue going this way? Well, the answer to that is it'll keep on going. You can actually get a number for 100 cuts. It'll be astronomical, right? You can get a number for 1,000 cuts. It'll keep on going. The number of cuts can actually keep on going. Hypothetically, in an exponential growth graph, you can actually get a very large number here. Okay, so the x value does not stop. Also going this way on the other side, right? We can keep on going too, okay? And this value right here, which started off as 1, it'll go to half, and then it'll cut in half to 1/4. It'll keep on getting smaller and smaller too, Okay, will it ever get to 0? No, it won't. But it will keep on going. Okay, it'll keep on going to the left and it'll keep on going to the right. Okay, so that's very important to understand. So, I could draw a little bit of an infinity symbol there so you guys can understand it'll keep on going from positive infinity on the right side and negative infinity on the left side. Okay, on the bottom over here, it'll never hit 0 on the y-axis, but it'll hit an astronomical number. It'll keep on going on the y value going up. All right, do you notice any trend in the data? Yep. We can say it increases. And it's slow at first, then increases quick. From slow to fast increases. Okay. Determine the pattern found in the y values of the table. Well, the y values are doubling. Okay, they just keep on doubling, literally. And here's another thing I could tell you, that if you divide the y values, you get a constant factor. Okay, if you divide the y values, you'll get a constant factor. If they're doubling all the time, then if you divide all those y values, 128 divided by 64, you get 2. 64 divided by 32, you get 2. You get a constant factor. This is a lot like what we did with the first differences when you're subtracting the y values, or the second differences when you subtract the first differences. But now, when you divide your y values, you actually get a constant factor. And this is the indicator of an exponential graph, okay? That if you divide the y values on, let's say, a table of values, right, in the y values of the table, you're going to get the same factor. Okay, it could be 2, could be 0.5, could be 3, whatever it is, but it will be the same factor. All right. It says, many real-world situations can be modeled using exponential relations. To determine whether a relation is exponential, you got to divide each y value by the preceding y value. Okay, if the factor or the quotient is the same, then we know it's exponential. Graphs of exponential relations are either increasing, that's getting bigger from left to right, and that's what we call growth, right? Or the graphs can be decreasing, getting smaller from left to right, and that's what we call decay. Okay, so if you're going from left to right, if they are going up, then they're growth. And that's what that looks like. It'll look like this, right? And it'll be on the other way, it'll start maybe high and it'll come down. That's a decay situation, maybe more like this. Okay, no, that went up first. Like that. That'd be a perfect decay situation. That's what you want to see. The equation of an exponential relation is in the form y is equal to a, okay, times b to the exponent x. Now notice that the x is only on the b, okay? A is what you start off with. That's your initial amount. In our piece of paper idea, the initial value is 1. We start off with 1 sheet of paper. B is the growth or decay factor, okay? If it's doubling, then guess what? We use 2, right? But b can't be 1. Okay, because something that's growing by a factor of 1 every time is actually not growing. It's staying the same. Okay, now here's a trick. If the factor for growth is a number that's larger than 1, remember it can't be 1. If it's larger than 1, even 0.1, right? Like 1.1, 2, 3, that's what the b value is. Then you have a growth factor, okay? And that amount is the amount that's added to the 1. Okay, that's how much it's growing by percentage. Over here, the decay factor is going to be a positive number, but it has to be in between 0 and 1. For example, here I could say the decay factor could be 0.5 or 0.2 or 1 over 3. Whatever that number is, as long as it's positive and it's less than 1 and greater than 0, you have a decay factor, right? And in that b value will be 1 subtract whatever this value is, and that'll give you the rate of decay, okay? you'll see that when we get there. Let me highlight that as well. That's a decay factor. Okay. An asymptote is a line that a curve continually approaches but never meets. Does anybody know where the asymptote is with our graph up here? Yep, it's right here. The asymptote is right here. Okay, the asymptote is y equals 0. Okay, because it'll always approach it, it'll keep on going closer and closer to it, but it'll never hit y is equal to 0. Okay, you can divide the number 1 as many times as you want, try it on your calculators, but you're never going to get 0. All right, examples. Determine whether the relation here is exponential. It says a bacteria doubles in number every day. Currently, there are 200 bacteria in the sample. Well, here I'm going to say yes. Yes. Okay, this is exponential growth. What about here? Sarah is given an allowance each week. Her allowance increases by $1. So let's say she's got $5 a week this week, but next week she's going to get $6. The week after that, she's going to get $7. Week after that, she's going to get another $1 on top of that, which is $8 for the week, then $9. Is that exponential growth? No, it's not. Okay, it is maybe a linear growth where we're increasing it by just 1 every time, but it's not exponential growth. Okay, so this is no. It's a linear growth. She started with $5 and we're just adding $1 every week. Okay, let's keep it going. A new car depreciates in value by 25% every year. The new car is worth $44,000 today. What will it be worth in 5 years? This is a very depressing thing to hear. But I've actually found mixed reviews from students when I talk about the value of a new car. Half of the students couldn't dream of getting a brand new car because like our Suzuki community, everybody here is from a working family, and a lot of people really are frontline workers or essential workers, and it's a tough life and everybody grinds it out. To get a new car is basically a fantasy for a lot of people, especially if you're in high school. So it doesn't really apply to them. They're like, ooh, a new car, right? Whereas some kids actually come from money and they're like, yeah, I'm supposed to be getting a new car. I can't believe that my parents still haven't given me that new car yet, okay? And you have those kids too. No judgment, but we are kind of in mixed bags here. But I do want you guys to see what's going to happen to a new car. You get a brand new car and it depreciates by 25% each year. The car starts off worth $44,000 today. A $44,000 car is a low-end Beamer, okay, or maybe like a high-end Hyundai, okay. $44,000 will get you a new car. What would it be worth in 5 years? So let's try to fill this out. It starts off $44,000. Okay, year 0. After year 1, it loses 25% of its value. So what would I do? Well, you want to take the 44,000, right? Let me write that better. And you want to multiply it by, well, you can multiply it by 0.25, which will give you the amount that it depreciates, and then subtract it from the 44,000. Okay, or you could just multiply it by what it's going to be worth. In this case, what it's going to be worth is 100% subtract 25. So it's going to be worth 75% of its value. Okay, and this will just give us the final answer. You guys catching that? Okay, so you can either multiply the 44,000 by 25% and then subtract that amount from 44,000, or you could just 44,000 times 75%, which will tell you what it's going to be worth. Okay, so if you do that, you get $33,000. You wait a year and buy this car. They'll sell it to you for $33,000. And you repeat it. Okay, you just keep on repeating the process and you fill in the chart. Wow, look at this car. After 5 years, The car is only worth $10,441.41. Did you have fun? Yeah. Did you drive it around to Wonderland and all these different places to be seen and stuff? I'm sure you did. But you just lost pretty much 30,000, 34,000 gone for 5 years worth of driving. Now, is this relation exponential? And the answer is yes. It's dropping by a percentage, okay, all the time. So the answer here, you're going to write yes. And we know that because the y values divide by 0.75 every time. Oops. The y values, which is the value of the car, decreases by 25% every time, every year, okay? And because it decreases by 25%, you figure out what that 25% is and you subtract it from that price. And really, you can just take the price and times it by 0.75, which will give you what's remaining, right? Is this relation an exponential, an example of exponential growth or decay? The answer is decay. Okay, all right. Write an equation to represent the car's value. Well, remember, we're trying to say y is equal to a times b to the exponent. Sorry, let me scroll back there. Y is equal to a times b to the exponent x. Okay, so a is the initial value, and b is the amount of growth or decay. In this case, this is a decay situation. So we know that we're going to write y is equal to a times here, which is 1 minus r as a percent. And we got that from just above when I highlighted it, okay? And then we got the x here. Okay, so if I fill it in, I'm going to write y is equal to my initial value of the car, 44,000, times 1 minus the amount of decay or the growth is 25%, which I actually have to write as a decimal, 0.25 to the exponent x. And let's bring it home with our final y is equal to 44,000 times 0.75 to the exponent x. Okay. Somebody could also say that the value of the car, instead of y, they're going to say v for value of the car is equal to 44,000, the initial value of the car, times 0.75, and to the exponent x, or the amount of years that we go by. Actually, I shouldn't use y because x and y are a part of that. I'm going to use t. Okay? And that's the same thing. What is it after 3 years? You plug in the 3 there, 0.75 to the exponent 3 times 44,000, and you get your answer. After 0 years, that's 0.75 to the exponent 0, which is 1. 44,000 times 1 is 44,000. All right, let's check out this graph. Okay, thanks, Mr. Chang. This graph is actually labeled this time. It says sketch a graph to represent the car's depreciation in value. Okay, so we're going to take a moment and plot in the points and connect them. And bam, right? Here's our graph. We just plotted in those values of the car, and you just take your pen and try to make a connected smooth line. It's a little bit of a challenge trying to do this on the surface. But you see this depreciating value. It starts off like it's depreciating fast, then the depreciation amount every year seems to be getting less and less, and that's because we are taking 0.75 of a smaller amount, so that actually works out to be smaller and smaller. So it starts off fast as it slows down, right? Ooh, we got a question about domain and range, right? Domain is the x values, right, that this graph will cover, and the range is the y values that this graph will cover. So when you think about the x values that this graph will cover, well, it starts off at 44,000. Was it ever even higher than 44,000? No. In this particular case, the x value was 0. We're going to start from 0. And we're going to keep on going because the x values, the number of years you can have this could be unlimited, right? So we are going to say that this belongs to the set of real numbers where x is simply greater than or equal to 0. Okay, what about the y values? The y values, the highest point for the y values is 44,000. The lowest point for the y values, if you guessed it, what's the least a car can be worth? 0. Okay? 0. Book value. So, how do you capture this? We're going to say y belongs to real numbers such that 0, y, and 44,000. Y is in between 0 and 44,000, like this. Okay? Can it equal them? Yep. And actually, in our graph, we cannot because we have an asymptote there. Okay? And we are stuck like this. It can't be equal to 0, actually. Your car cannot be equal to 0. The cheapest you can sell a car and transfer ownership is 1 cent, or maybe $1. It goes with houses, too. It's an interesting fact. So that's that. You guys have some homework practice, and that's page 83, and the questions are on the outline, so have at that, and that's that. Hope you guys are all doing well. Stay tuned for the next lesson. Goodbye.